Okay, so let's start. In the last class, we proved this theorem, which said that as long as you have a PDS kernel, there exists a Hilbert space, which would have any number of dimensions, and a mapping from the domain to the Hilbert space, such that the kernel acts as an inner product within that Hilbert space. Right. So this essentially allows us to evaluate inner products over the Hilbert space just using the kernel, which is a map on the domain itself. Okay. Now, although it told us that there exists such a mapping, it doesn't really tell us how we can perform learning efficiently. In fact, we'll see a more general result, which goes beyond just classification. It says that any optimization problem that can be framed in a suitable form, which includes, say, support vector classification, support vector regression, and many other problems, all of it can be solved efficiently using these so-called, or at least there exists a solution that can be expressed purely in the form of the kernel itself. Right? I'll make that more precise as we go along. Okay, and this Hilbert space, what the kernel maps to, is a special. I mean, there could be multiple such Hilbert spaces. This mapping may not be unique, but if we ask for some more properties in that particular Hilbert space, then it turns out that this mapping and the Hilbert space for a given kernel is in fact unique. So in the last class, I defined this so-called reproducing kernel Hilbert space, which said that which is any Hilbert space of functions from a domain to the set of reals, such that the evaluation functional is always bounded for every single x. Right? But I mean, this definition doesn't seem very intuitive. So in fact, there's a more intuitive definition or an equivalent property of RKHS, which is the following. So we say that a class of functions or a Hilbert space of functions so it's a subset of the set of all functions from some domain to the set of reals is a reproducing kernel Hilbert space if this Hilbert space has the following reproducing property. So there exists, so for each x in the domain, you can find a function a subscript x such that the inner product of any function from this Hilbert space with this kx is simply the evaluation function. So this inner product essentially can be evaluated just by taking the evaluation of f at x. So in the previous construction, when we started out with a kernel and constructed the reproducing kernel Hilbert space, you can verify that if you take any function, so let's start with this kx belongs to the Hilbert space. It's some function, it is some function that depends on x. It could be any arbitrary function. And the inner product, so essentially you can find f of x by taking the inner product of f with this particular function. So we have a Hilbert space, right, which means that the Hilbert space has its own inner product. When I say a Hilbert space, it's a vector space with an inner product, right? So this inner product is inner product over the Hilbert space, whatever it may be. It could be anything. It could be, I mean, again, it could be any Hilbert space of functions, right? So for example, so you're given a Hilbert space, right? If it satisfies this, then it's called a reproducing kernel Hilbert space, right? And essentially you can use this kx to define a kernel for the RKHS, right? Remember that this Hilbert space was originally not defined using a kernel, but this kx in some sense lets you or helps you find a kernel that corresponds to that RKHS. So if we go back to the construction in the theorem, let's quickly recall what we did. So effectively, we were originally given just the domain and a kernel over this domain, and we defined functions px as k of x comma the second argument being free, right? So this defines a function, right? And we define the inner product between two elements. So the Hilbert space that we started out with was a linear combination of these phi x, right? All finite linear combinations. And the inner product was defined as a linear combination of k of xi xj's. Correct? So this holds true for all f comma g in h naught. Right? In h naught, every function is a finite linear combination of the phi xi's. Correct? In a reproducing kernel Hilbert space, this holds true for all f, even if all f in the Hilbert space h. And in h, you don't necessarily have so it need not be just a finite linear combination of the phi xi's, right? Because we essentially define h by completing h naught. So all convergent sequences of phi xi's is also a valid element in h. So if we go back to the construction, then for any f in that Hilbert space that we constructed and any x in the domain, we have the inner product between f and the function kx or k of, which is nothing but the inner product between f and px. This just evaluates to f of x. So that's one way of stating the reproducing property of the RKHS. So one thing to note is that not all Hilbert spaces of functions forms an RKHS, but the class of RKHS is very rich in the sense that it's very difficult to come up with an explicit example of a Hilbert space of functions which is not an RKHS. So pretty much any Hilbert space of functions that you can think of will be an RKHS. Proving that it's an RKHS might be difficult, but it will be an RKHS. There are other techniques in analysis that you can use to show the existence of Hilbert spaces that are not RKHS. Which one? F belongs to H. That's the property. So K of X comma H whatever dot, this lies in H naught, which means that it also lies in H. But F can be any element in H, not necessarily in H naught. We proved that H is a Hilbert space, right? So H naught was a vector space, and we defined the inner product over this Hilbert space, but it need not be complete. So we constructed H by adding all of the limit points. So H is the RKHS because it has to be complete. It's not even a Hilbert space otherwise. H naught is a subset of H. It's an inner product space. So for it to be a Hilbert space, it should also be complete. Right? Every Cauchy sequence should converge. That may not happen in H naught. Yeah, with all the limit points, is basically an RK. That's the definition of H. H naught need not be anything but
it's not in the inner product space.
Correct. Yes.
It is also that specific.
Exactly. It's the same inner product. Everything is the same. It just has a few extra points. Correct. I mean, you can construct a number of Hilbert spaces. You think of any Hilbert space. So, for example, set of all, let's say, band limited functions with the inner product being integral from minus infinity to infinity f times g. Yep, set of all L2 functions. So that is all square integrable functions.
Or set of our random the expectation.
Sure, yeah.
That will be RK.
But will also be an RKHS. Proving that it's an RKHS is hard. Finding that kernel may be hard. Right?
Is there any creation?
Again, may not be explicit.
Means we need to come up with a function which that property or
correct.
For the fixed.
Yes. For every x, you have to find a function kx such that what is this inner product may be equal to f of x. In some cases, it may be easy to find such a kx. Sometimes it may not.
Kx.
I'm not saying anything at this point. Which one? So at least for our purposes, we don't care about arbitrary RKHS, right? For our purpose, we're given a kernel, we pick a kernel, and all we need to know is that there exists an RKHS corresponding to this kernel. That's it. Right? And again, how do you choose the kernel itself? It's not evident, right? Because your kernel will essentially define the hypothesis class, right, or which you want to learn, and that hypothesis class, again, usually the choice of kernel depends on whether you have some background information about the problem that you're trying to solve. For example, if you know what kind of a classification problem, let's say you know that they might be polynomially separable, or a polynomial classifier may work well, then you just choose a polynomial kernel and do SVM. But in other cases, that may not be true. If you don't know anything about the problem at all, then you would have to choose an arbitrary kernel and hope that it works well. In many problems of practical interest, people find that Gaussian kernels work well. But that's just an empirical result. You can't really prove that it's going to work all the time. I'm sorry?
What is your point?
So we will not find the RKHS. All we need to know is that there exists an RKHS corresponding to this. Why we're interested in RKHS specifically, that will be clear enough. All right. So sort of. So just a moment. So the reason why we would like it to be an RKHS is the following. So it comes from the following result called the representative theorem. So suppose I have a kernel and let's say H is the corresponding RKHS, and G be any non-decreasing function and L be any loss function. So L need not necessarily have the form of an empirical risk, but it could be anything. So if I have an optimization problem which is of the following form, so I want to find R min over all possible H in this RKHS, and the objective function takes the following special form. So it is G of the norm of H. The norm is of course the norm over the Hilbert space plus any function that is of the form H of x1 h of x2, h of xn. Right, so as long as I have an optimization problem, a minimization problem, that of any objective function that's a non-decreasing function of the norm of h, and something that can be written as h of x1 times some function of h of x1, h of x2 up to h of xn for any n elements in the domain. Now, definitely the SVM problem, kernel SVM problem, can be stated in this particular form. And a lot of other problems, including regression, can also be stated in this particular form. In fact, regression along with a regularization term can be expressed in this particular form. So any such problem has a solution h star, which is just a linear combination of k of xi which is nothing but summation I equal to 1 to n alpha I p xi. What do you mean that's specific inner product? Correct. The inner product with respect to h naught is the inner product with respect to h. Both of them have the same inner product. Yeah. So I'm saying that there's only one RKHS for a given kernel, right? We have not proved that it is the only RKHS, but that's something you can prove. Is exactly what we did in the construction. Right? F, what is F? That's for a specific choice of alpha. I mean, this is all I'm saying is that the solution is essentially a linear combination of k of xi, which is what we have in the SVM problem, the kernel SVM problem. For the kernel SVM problem, essentially what this theorem says is that the optimizing h star is a linear combination of the support vectors. That's it. But more generally, even if I have, let's say, a regression problem, the solution to my kernel regression problem is again going to be a linear combination of the k of xi's, where the xi's are the data points from the training set. Okay, so if I'm somehow able to find these alpha i's, okay, again, it's not clear how I'm going to find these alpha i's, but if I'm able to find the alpha i's, then I have a very nice form for the predictor, because everything is in terms of the kernel, nothing else. If I'm able to find the alpha i's, I find the h star. Whatever, order of n complexity. I mean, order of n times the complexity that is required to compute k of x1, x2. Okay? Because the xi may already be a high dimensional in a high dimensional space, but the complexity is independent of the dimension of h, because I don't need to perform any computations in h. That's the nice property. So at least this statement says that if G is non-decreasing, now there could be multiple H, like H, which minimizes this particular quantity, and there exists at least one H star which has the following form. But if G is strictly increasing, then every solution has the above form. So this is a very general optimization problem. One of the solutions can be expressed as a linear combination of the phi xi's. If G is strictly increasing, then every solution will be a linear combination of the phi xi's. All right. The proof is fairly simple. Essentially, so you consider, so suppose that H is H prime be the span of phi x1 up to phi xi. The claim is that the solution to this optimization problem lies within this span. So this is a vector space, right? So H prime is a vector space. It's a vector subspace of H, right? Which means that any H that lies in the bigger Hilbert space can be expressed H equals H prime, where H prime lies within the span, plus a H perp, so one that lies within H prime and one which lies in the orthogonal complement of H prime. Right, so this lies in H prime and this lies in the orthogonal complement of H prime. Okay, so let's look at L of first. Let's consider H of xi. Okay, for any xi. Now we know that H is an RKHS, right? So what does the representative theorem say? Right, so let's go back to this this particular property. So f of x can be written as an inner product of f with phi x. Correct. So h of xi is nothing but an inner product of the function h along with pxi, right? But I know that h can be written as h prime plus h perp. Which is h prime pxi plus the inner product between h perp and phi xi. Keep this as it is. What is the second term? It's 0 because h perp lies in the orthogonal complement of h prime and phi xi lies in h prime. But what is the first term equal to? It's okay. I mean, it's just h prime of xi, right? Right? Which means that the second term in my optimization problem, L of h of x1, h of x2 up to h of xn, this is equal to L of h prime of x1, h prime of x2, so on up to h prime of xn. Okay, that's one thing. So that takes care of the second term. Now let's look at the first term in the optimization problem. So I have h, so I have whatever g of the norm of h. All right, this is nothing but g of, let me first consider g of h prime. Okay, this is less than or equal to g of h of h prime square plus h perp square under square root. Why is that true? G is non-decreasing. So the norm of h prime is less than or equal to the square root of norm of h prime square plus norm of h perp square. And G is a non-decreasing function. And in this case, we have strict inequality if G is strictly increasing. Right? But what is this equal to? This is G of the norm of h. Right? So the objective function for any given h is greater than or equal to the objective function with h replaced by h prime. And h prime lies in the span. So you might as well, instead of looking for the optimizer over all of H, you might just look over all of H prime. So the minimum of the objective function over all H in H is in fact equal to the minimum of the objective function over all H in H prime. So that's it. Now this representative theorem, it tells us that the solution can be expressed as a linear combination of the phi xi's, or you can always write it in the context of classification. H prime, H star, even for kernel SVM, is a linear combination of the support vectors. But it doesn't tell us how to find those support vectors, or it doesn't tell us how to find these alpha i's. For that, we have to come up with our own algorithm in order to perform this efficiently. Right? Yeah. Okay, it's a good point. So in this case, potentially there could, like, if G is non-decreasing in general, then the objective function for a given H, which does not lie in H prime, could be same as the objective function of some other H prime that lies in H prime. Correct? So there could be multiple solutions. If it is strictly increasing, if G is strictly increasing, then the objective function, right? So if G is increasing, then just by this property, note that if G is strictly increasing, then G of H prime is strictly less than G of H, right? So the objective function of corresponding to H is strictly greater than the objective function for H prime, which means that you can't have a solution, you can't have a minimizer that lies in H but outside H prime. Right? Yeah. We don't, at the moment, we don't have an advantage because we don't know how to do it computationally efficient. Right? Now, there's a lot of theory behind all of this, and we don't have the time to cover all of it. So I'm just going to present an algorithm, a stochastic gradient descent algorithm, without telling you how I derived it. So we'll first go back to the standard SGD for SVM, all right, and just extend that to an SGD for kernel SVM. So you can see chapters 14 and 15 of the Understanding Machine Learning book, the book by Shai Shaleb Schwartz and Shai Ben David. So that has more details on how this is derived and so on. Okay, so recall that the optimization problem was the following. For SVM, we wanted to minimize norm a square. It's a slightly different variant. I'm just playing around with the coefficients a bit. So we want to minimize lambda by 2 norm a square plus 1 over n summation I equal to 1 to n times the hinge loss 1 minus yi inner product of xi. And I'm looking only for homogeneous solutions, so b is set to 0. Okay, so the algorithm is as follows. So you initialize vector theta to be equal to the 0 vector in Rd. Then for t equal to 1, 2, 3 up to, let's say, t, capital T time steps, we do the following. You compute a t to be 1 over lambda t times theta. Let's see, let me initialize theta 1 to be equal to 0. So at is 1 over lambda t times theta t. And you pick I uniformly at random from 1, 2, 3 up to n. So you pick one of the data points uniformly at random. And you set theta t plus 1 in the following manner. So it's equal to theta t if yi times the inner product A transpose xi is greater than or equal to 1, and it is equal to theta t plus yi xi otherwise. You run this for t time steps, find the ATs, and finally you just output the average. This is essentially a stochastic gradient descent algorithm for finding the SVM, the soft SVM problem. So we want to do this, we want to perform this minimization, which could in principle be done using gradient descent. And this is just a stochastic gradient descent algorithm for the same. Right? So I'm sorry, can you repeat? Correct. But then it depends on how you choose the stochastic gradients, right? As we saw, there are multiple ways of defining the stochastic gradient, and this is one specific way of doing that. All right. But this is in a specific form, in a nice form, that we can very easily extend to kernel SVMs. All right. And the reason why it's helpful is because now everything is completely expressed in terms of the inner product and the yi. I need nothing else. All right. The random variable is you pick I uniformly. That's why it's a stochastic gradient. It's not a mini batch SGD. You can interpret it as a mini batch SGD with batch size equal to 1. Right? But also, this doesn't have a constant learning rate, which we were sort of assuming previously. Lambda is a hyperparameter. We just fix lambda to be something and just work with it. That's why. So I don't want to get into too much detail of this. That would require an entire derivation of this particular SGD. But I mean, intuitively, you want the learning rate to sort of decrease, so that as you get closer to the original solution, you don't jump around too much. But why this specific learning rate? That requires some more details.
Initially, theta t will not be.
Initially, theta t will not be accurate. That's
We are
true.
giving more weight to initial times. T tends to T, capital T.
Correct.
The AT value will be very less. T will be high.
That's okay, because we're implicitly assuming that T is very large. So you have this 1 over capital T, which will get rid of the first few terms. That's how it goes. Right. But even otherwise, I mean, this is what we are going to take as the solution, because this can be analyzed easily. But in practice, you don't do this averaging. You just take the last value of A. That's it. All right. Okay. Any questions? All right. Let's go ahead and try to see how this works. Okay. So here I've generated some data according to a certain distribution. So all of the data points will lie between on the plane or on the square region between -1 and +1, x and y values between -1 and +1. So if I plot this out, this is what it looks like. So my data set is not linearly separable, but most of the points that are labeled +1 are above the line x1 equal to x2, and vice versa. Most of the points that are labeled -1 are below the line x1 equal to x2. I'm sorry, x1 equal to -x2, not x2. So I'll try to implement an SGD. I'll try to implement the same algorithm for 100 time steps, t equal to 100. I'll choose lambda to be equal to 0.1. So what do I need to do? I need to initialize the vector current. And I need to store the ATs for every time step t. So the first step is we have AT to be equal to 1 over lambda times t. I mean, in this case, t plus 1 times that's correct. I'm sorry? Can I increase the brightness? Oh, okay. I think you'll have to turn off the light. Is it okay now? This times previous, and I'm going to pick an I which is uniformly distributed between 0 to n minus 1 and set theta current to be equal to theta previous. But if yi times the inner product between at and xi is less than 1, right? So theta t plus 1 is equal to theta t if if yi times the inner product between a and xi is greater than or equal to 1, but it's equal to this if this quantity is strictly less than. Previous times at. If this is less than 1, then plus yi times x. Not I just leave it as it is. And in the end, I also need to right. M is equal to at right. See what happens, and let's try to plot I'm sorry. Oh, that's right. should be divided by t. I'm sorry? Yes. We take the sum over 8t's, yes. So the AT is basically going to be the classifier. That's going to be the hyperplane classifier. There is no P. Okay, let's see what I get. I run this specific SGD algorithm and I get the following classifier. All right. Again, it's a homogeneous classifier, which means that it has to pass through the origin. Okay. And it doesn't seem to perform too well, but of course we have to keep in mind that the data is not linearly separable. If the data were actually linearly separable, again, it's a soft SVM, right? And we're running SGD, so this is not guaranteed to give you if you increase the number of time steps, it kind of gets closer to the actual solution. But if I decrease this to 30, it may have missed, let's say, some of these points in the train during the time of training. Again, we're only using one sample at the time of training, so it's possible that some small fraction of the data set is completely missed out. Now I can try to compute the generalization error. I can generate a test data set. Let's say I have 1,000 or 2,000 test points. So y is, so y is -1 step by step. So if a SVM times whatever a SVM transpose x test is greater than or equal to 0, then this is equal to +1. And if it is less than 0, then this takes the value -1. And the loss is just 1 over m times y out is not equal to y test. It achieves a generalization error that is around 0.1. Go back. Okay, so this is non-separable data. And it achieves a generalization error which is 0.219 something, right? So this allows us to whatever design an SVM, but in itself it's not the best algorithm to design an SVM. But what it helps us is in designing a kernel SVM. So here's an SGD for kernel SVM. This is almost exactly the same with some minor changes. So now I can't explicitly find the vector A because A lies in this higher dimensional space, potentially infinite dimensional space, right? So in this case, you need to do two things. So first, you have to compute the kernel matrix. If I need the kernel matrix, and I'm going to maintain a vector alpha in R to the n. So these are going to be the coefficients of each of the phi xi's. Right. So immediately you see that at least this variant of SGD for kernel SVM grows quadratically in the size of your data set. So if your data set is large, your computational complexity is also fairly large. So you initialize as before, we initialize theta 1 to be equal to 0, which is going to be in Rn instead of Rd. And alpha t is just going to be 1 over lambda t times theta t as before. I'm going to independently choose a uniform I between 1 to n, and I will set theta. I'm only going to modify the ith component of theta t. So this is going to be equal to theta ti if yi times, again, the inner product between a and the xi's, a and x is greater than or equal to 1, and xi is greater than or equal to 1, then I should be keeping it the same. Instead of that, it's going to be a summation j equal to 1 to n alpha j k xj xi. Right, so this is effectively a replacement for A transpose xi. If this is greater than or equal to 1, and it's equal to theta t I plus yi x, and theta t plus 1 j is equal to theta tj for j not equal to I. Yeah.
Basically, we are taking
So ideally, yeah, if you are doing it in the feature space, which is your RKHS, but you're doing it without going to the feature space. You're doing all of the evaluation in your base space itself. Computational complexity, right? I have an algorithm that does not scale with the dimension of the feature space. It's independent of what the feature space is. I don't even need to know the structure of the feature space, right? H, the RKHS H. Because effectively, where does the linear classifier lie? It lies in H, right? I'm designing a linear classifier in H without explicitly going to H at all. It corresponds to some linear classifier in that space, but in the end, I don't need to know what the linear classifier is. All I need to know are the alpha j's, right? Just the coefficients of the support vectors. That's it. The support vectors, yes, they lie in the higher dimensional space. We don't, right? We don't need to. That's the whole point, right? All I need to know is k. K of xi xj is computed within x. Correct. So I'm giving you an algorithm to find the coefficients. Yeah. So what is the final solution? So your final alpha is 1 over t summation t equal to 1 to capital T alpha subscript t, right? These are the coefficients, and if you went to the higher dimensional feature space, then your a t or whatever a would just be summation I equal to 1 to n alpha I times pxi. This a belongs to H. But I never need to work with this A at all. All I need to know is alpha i's. Because at the time of prediction, again, I don't need to explicitly multiply A with an X, right? So my predictor is going to simply be is just going to be indicator summation I equal to 1 to n alpha I k of xi comma x greater than or equal to 0 for a given x. That's it.
Generally, it is actually A transpose.
Yeah, so what would it be? It would be indicator, whatever, it's going to be an inner product, right, between A and k of x. A and k of x, right? X lies in the domain, but k of x lies in the feature space. Or this is if you're not comfortable with this notation, is going to be with phi x. Yeah. Right. This is what is happening, but you don't need to compute this. I mean, or in other words, you can compute this inner product just by using the kernel. Yeah, the computational complexity doesn't depend on what the feature space is, right? The feature space is an infinite dimensional space in general, right? I mean, A is a function, right? So how do you find the inner product between two functions? Correct. You'd have to compute an integral, right? In general. Okay. Can you compute the integral exactly? Yeah. But here, can you compute the inner product exactly? Yes, because I can compute the kernel. I can evaluate the kernel. Can you repeat?
The value which has been.
Yeah, it's the same, right? This is equal to the inner product. That's the nice property of RKHS. What is always the case? Yep, that's the whole point, right? That's what the representative theorem tells us. Right? Of course, what the representative theorem slightly misses out is the prediction part, right? Because it doesn't care about what you're using the solution for. But if you can make a prediction that purely depends on the inner product between that solution, the solution to the optimization problem, with some phi x, then you can also do the prediction very efficiently. Right? Okay, let's see if I can try to implement this quickly. Okay, so first I need to compute the kernel matrix. Okay, just by n matrix, and say I use the Gaussian kernel. Let's do something quick and dirty. So k of ij is e to the power of minus, let's say, sum of xi minus xj the whole squared. So x I minus x j square. I have an np dot sum, and I need to divide this by, let me take sigma square to be equal to 1. Okay, so now I have my k. In this case, the thetas are n-dimensional vectors. Alpha is equal to this. Alpha is this, and zeta current is equal to zeta previous. This I have to change. So effectively now, if rewrite this, so I have if yi times summation j equal to 1 to n a alpha j times k of xj xi. T minus 1 along with have the kernel matrix. This is with the ith column. Is less than 1, then right. So I pick an I uniformly at random, and all the other coordinates remain the same. Only the ith coordinate is updated to theta t I plus yi if this quantity is strictly less than 1. SVM is, hope that this is correct. It's something. Now I have a huge data set, and what I can do is try to plot and see how it would classify. So out, this would be by out of, and to evaluate, just for each data point, each test data point, and for kernel I have to equal to, so I have to look at summation alpha j I times the kernel, which is I want the prediction for the corresponding, for the jth test point, and remember that I want to express this. This is what I want. For the jth point, I have to evaluate this particular quantity, and in the end, y out of j, this is equal to 1 if it's greater than or equal to 0, then you output a 1, and j, this is equal to -1. Let's just m equal to test, and I'll also want to plot what this looks like. I'm sorry. Yeah. No, it's greater than or equal to 0, right? If the inner product is greater than or equal to 0, then you declare it to be, it's a homogeneous classifier, right? That's why it's greater than or equal to 0 instead of greater. Yeah, and so this is, I'm trying to perform the predictions here. It's greater than or equal to b, yeah, right? Okay, let's just see this. Not worry about this. Oh, yeah, this is how the SVM would perform. It's not exactly a linear classifier, because this would be sort of curved. Yeah, this is for the test data. You can't plot it, right? Because it lies in a higher dimension.
Then what if
I'm sorry. It's going to be an infinite dimensional space, right?
it's previously we started with IDs and mapping
I'm sorry.
previously we set the map transfer
Correct.
R.
Correct. Well, that's assuming that you can find a feature space of finite dimension. But in this case, the RKHS is going to be an infinite dimensional space, right? Remember that the mapping was from x to r to the power x, set of all functions on x, right? So it is a set of all, it's a subset of all possible functions on R2, which is going to be an infinite dimensional Hilbert space.
To a finite space. If we get it fixed,
You can't, right? But again, you don't need, you don't care about it. That's the whole point of a kernel method. You don't care what dimension the actual solution lies in. You perform all the computation in a much smaller dimensional space.
that transforms.
There is no guarantee. There is no guarantee. But then you're designing a linear classifier on that RKHS. Yeah.
How do we actually pick up there's like this algorithm to see them?
Correct.
How do we?
It's not clear. So in general, that's why there's a lot of research where for each problem you sort of hand design a kernel that works well. But in many cases, it's not clear. The first thing that people start out with is you just you just choose either a Gaussian or a sigmoid kernel. So you take a tan H function or you take the Gaussian kernel, see how it works. That's your baseline. And then you design something more fancy. Yeah. Yes. Yes. Any other questions? Okay, let's stop here.